Topology. Can you hear me? Hello?
Yes, sir.
My screen is visible or not?
It's visible, sir.
Okay, fine. Okay, let me start. Last time I talked about subspaces. Okay. Create new space. Okay. So next time I will talk about product space. Product of topological spaces. Product spaces. But before that, remember that how it got subspace. If you have X tau and Y is a non-empty subset of X, okay, then Y tau Y. That is called the relative space or subspace. This topology is called the relative topology, subspace topology, or topology induced by tau. Tau Y was this. Okay. Now with respect to subspace topology, two things should be clear. First, suppose you have the function between two topological spaces. First thing, suppose this is, don't confuse with this Y. A is a subset of X. So notation F restricted to A. It is a clear meaning. That means this function when you are restricted. So if A will be a function, then you can need to consider this topology, tau A. So it will be a function, again this. It can be shown just by using the definition of continuity. If this is continuous here, this will be continuous. So let me write the first result. You should prove it. So that result one is let X tau is Sarthak is here. You should listen to me. After let, I once I discussed it should be root one. So let B, it is you all the time keep using is. Let X tau be a topological space. Oh, sorry. Let F X tau Y sigma be a continuous map between two topological spaces. And non-empty subset, then F restricted to that, then F A is also continuous. Look, inverse image of an open set in Y. Proof is very simple. Let V belongs to sigma. Then you see that you can easily check that this it's inverse. V here has to be F inverse V, but you are restricting to A, so it has to be intersection A. But this is belongs to tau, since F is continuous. So that this belongs to tau. That exactly needed to prove. So I have given the proof actually. Okay. Now but this is very simple. That means any continuous function restricted to a subset will also be continuous. But now listen to me. This is more important. Suppose we have this function. Suppose f is not onto. That means fx is a proper subset. It's called proper subset of y. Then f is also a function from x tau to this. And here topology will be this. You can check if this is continuous here, this will be continuous here. Okay. The other way also, suppose this is contained in a bigger space for which y is a subspace, then it will be also continuous. Let me write what I am saying. Result 2. Let fx tau by sigma be a continuous, actually be a map. Let me just write. Be a map. Okay. Right. Which way I should take that? Which way will be more important? Okay. Now let me write this. That will be something. And let tau sigma to take Z alpha be a space, be a topological space such that, see that what I'm writing, such that y is contained in Z and this is alpha topology restricted to y, that is subspace topology, is same as sigma. Okay, let Z alpha be topological space on this. Okay, then can prove then f here x tau by sigma is continuous if and only if this is again the definition of subspace topology. You can do that. If you assume it is continuous, that means F inverse V, where V is open in sigma, that is open there, then you can prove there also. Okay, so I'm leaving it at exercise. That means it doesn't matter whether it covers the whole thing. Basically, it doesn't matter it covers the whole thing or not. That means this we say that range is immaterial. Of course, as long as you have the same topology. In the sense, if you are having a subspace, you are having a subspace topology. Range immaterial. Look, examples you have already used often in the real calculus, but you never bothered. Like here, suppose I have a function. This I can take as a function like this. Okay, right? Also, I can write this. I can take these as also function as this. Here you have the topology on whole R. Here, though I'm writing, is the subspace topology. Look, it doesn't matter which way you take, whether you take this or this, it is always continuous. So range is immaterial. Keep this in mind. This is a good thing. But the previous result, make sure that I have given only one way. If it is continuous on the whole space, that it is continuous on any subspace, not the reverse way. Reverse way, need not be true. If it is continuous on a subset, it need not be continuous on the whole thing. Okay, so that from you can take from here that the example. Okay, so that this thing you should remember. Now I want to study the spatial map, that homeomorphism. Homeomorphism. It is not. I think last semester I mentioned this word, homeomorphism. Here it is not group homomorphism. Here one extra is there. In fact, with respect to this, you should go to the net to know the real meaning of topology. Topology is there is a meaning that of the word, why it is called topology subject. Know the meaning of the word. Topology. Okay. Well, in order what we need to understand, basically it's a classification of topological spaces. Like in group when you had isomorphism. And there are classification of isomorphism, because isomorphic groups are essentially same. Like to have a group of order 4. Take. You know, it has to be abelian. Basically, it has to be either Z4 or Z2 plus Z2. Here it will come. This is actually Klein 4 group. In a group of order 4, you have only 2 groups. This is a classification up to isomorphism. That means, okay, because isomorphism means isomorphic groups basically they are same. Like in isometry you did in metric space. Basically they are same space. Only you are changing the place. You are renaming. Similarly here, the among topological spaces you would like to see that. The reason is very simple. That suppose I am having a space. If I can, what do we use? But first of all, I need to say what is homeomorphism means. That I'll have to mention. But then suppose I find another topological space where I see that whatever this property has this property. Don't think about the completeness because there's a metric property like separability, second countability, first countability, compactness, connectedness, everything. Whether they are shared by each of them. Okay, then you may think that this space actually is same this, but here probably the description is easier. Description of the space is easier. Then of course you will use this. Okay, now homeomorphism. Now I want to. That means how will you go for classification of topological spaces? So basically, idea is the classification of topological spaces. Idea is like the groups so that I would like to go for simpler description. Now look, when you have this, also when you have the continuous function, first of all, if I want to go for classification of spaces same, that means there has to be a one-to-one correspondence. That means bijection. That has to be, should be. But before that, you see that for what about continuity? Continuity you got F inverse V belongs to sigma, sorry, belongs to tau for all V belongs to sigma. Look, in topology, not only I have a map, I'll have to identify the elements. I'll have to identify the open sets also. Now look here, for each open set, you are getting an open set. What about other direction? Suppose straight here, that U belongs to tau implies, it did not be true, implies AFU belongs to sigma. Now in straight direction, this is the actual opposite direction, reverse direction I'm taking. Inverse image of an open set is open here. Here the image on open set in X is open in Y. So now suppose if in addition is a bijection, then look, I can identify X with Fx first of all. Now suppose I have these two, continuous and this. That means what happens? That means correspondingly this F will give you a bijection between tau and sigma. F will give you a bijection between the open sets. This will be this. Suppose you have these two. Then this will be a bijection. That means this will be a bijection not only between these two spaces, continuous and this thing. Then I will have a bijection between the open sets. That means in this case, X tau and Y sigma you can identify. Basically, in this element you will call Fx, and open set you call it Fu, the new name. So if you forget F and that, then basically the same thing. So in this case, X tau and Y sigma will be same. But that means I am having a bijection between the elements. Not only that, I am having a bijection between the open set. And in order to have it, I need this thing, the open map. So and that actually called homeomorphism. So that let me define first open map, this one. In function analysis, next semester we'll be doing at that. That is the Banach's open map theorem. That's a big theorem. Okay, so definition is let. Okay, I think I can try this. A map F X tau Y sigma is called an open map if Fu belongs to tau, sorry, sigma for all U belongs to tau. That is, Fu is open in Y whenever U is open in X. That means it belongs to this. This is called open map. Okay. But so first let me define the homeomorphism. So that definition. Okay. A bijection F X tau to Y sigma is called Be careful. Don't forget to put E. Homomorphism if F is both open and continuous. This is definition. So let's look at this definition carefully. Okay, F is both open and continuous. It's a biaxial. So element, you should understand element. These are the identification, and among the open sets, this is the identification. That means not only we are look in topology क्या है, only the एक सा set है, उसके साथ एक topology है, the collection of open sets, and that exactly on the other side I am doing that. I'm renaming X by Fx, renaming open set U by Fu. Okay, right? And there you say why I need continuity. You need continuity because while coming back, okay, there's one-to-one correspondence. So that this is called homeomorphism. Now you see you can easily prove that small result. A bijection F X tau to Y sigma is open if and only if. Look, it's a bijection, so F inverse is defined. So F inverse is a map from Y sigma to X tau is continuous. Look, here this is easy because F inverse of inverse, F is going here. If you take A is a subset of X, then it will be same as FA. Sorry, it will be what? बताओ, A or FA? Look,
FA.
F and F inverse, they are inverse to each other. So inverse of F, this is F. Okay, right? So this you'll have to note. F and F inverse, this is simple maps things. They are inverse to each other. So F inverse, its inverse is F. So using this, it is this. So that basically bijection means homeomorphism, you are doing it. What do we mean by that? What we want to do actually topologically? You want to move continuously from here, from X to Y. That's fine. But I want to identify the spaces. That means I should have the reverse direction, that when I come back, I need to move continuously from Y to sigma. For that, I need F inverse to be continuous. Okay, that's the idea. So actually, this idea of open map came from here. Okay, so that homeomorphism, you can definition, you can write. Alternately, you can write this definition, this. A bijection F between two topological spaces. It's a homeomorphism. That's the definition I have taken. Both open and continuous. Now I'm giving this. You can put definition or you can put as a result. Okay. Bijection is between two topological spaces is homeomorphism if and only if both F and F inverse are continuous. Look, some people take this as definition homeomorphism. The other thing that open they give it as a result. I have taken that definition, so I am giving it a result. But they are equivalent things, so I can write that. That I write. But if here you look, if you have a bijection, in the definition, when I had the equivalent characterization of continuity, you look, remember that continuity, recall. F is continuous, this also we got it. If and only if F inverse C is closed in X tau whenever C is closed in Y sigma. You could of course ask that why I had preference over open. I do not have preference. You could take this as also definition. That means this one. Okay, that means you could define closed map. Closed map, what I will define? The map, second different F between two topological spaces is called closed. If from here to here it's closed. If, don't confuse with this, so I'm writing it. If FA is closed in, this is continuous, so I am corresponding to define closed map. Closed, if FA is closed in Y sigma, whenever A is closed in X tau. This is called the closed map. Okay, so that means other than, look, that means what I have defined. Other, before we defined continuity. First you could define continuous map. Then you could define open map. This you should make sure you want C, closed map. That means it sends open sets to open sets, it sends closed sets to closed sets. And finally, homeomorphism. But here you need bijection. Okay. Now look, for this homeomorphism, that in case you feel confused on that, okay, I can write this way. Let me write this. What I would write. Then it will be clear to you. Like result. I'm not using any definition. I'm writing late F X tau Y sigma paired by action. It is one-to-one correspondence between two topological spaces. Then the following are equivalent. I have taken bijection. F is open. B, F is closed. See, F inverse is continuous. So from A open to closed, you see, if you take C closed, suppose C is closed, don't confuse it that sometimes I've taken it closed in Y, closed in X, then X minus C is open in X. If you have A, then Fx minus C is open in Y, but this is a bijection. This is Fx minus Fc, which means Y minus Fc. So Y minus Fc is open. That means Fc is closed. Then, but for bijection, these two are equivalent. And F is open, it's a bijection. So if inverse is defined, so F inverse will be continuous. So that look, homeomorphism, what are doing? Bijection, continuity. So I can, these are equivalent condition. I can add any one of them. That exactly people do. People usually do either they add this or this. So that's why in the homeomorphism, the bijection, first of all. Homeomorphism, the bijection, and also continuous first. Make sure that continuity is the minimum thing you require. But I want to, this basically tells you to move from X to Y, but I want need to come back also. If I want to identify, that means F inverse should be continuous. But that is F is open. So that F inverse is continuous. So that for definition of homeomorphism, you can take any one of them. But if they are not bijection, they may be all different. Okay, anyway, if it is not a bijection, then it won't be defined. But still you can define open and closed. So I am giving an exercise. What exercise I am giving? First, find a map R2R. Or you can take an interval if you want. I won't mind, which is continuous, but not open. 2. Find a map. The other way. Don't confuse with that. You can take it G if you want. Which is open. Actually, this problem, if you can solve it, this you will be able to solve it, because only thing you'll have to come from the other direction. Okay, then that will be open but not continuous. And here, find a map H R to R. If you do it on the interval or something different, like if you take this, that will be all right for me. Okay, find a map H R to R such that H is open but not closed. Map. Similarly, you do for this. For between continuity and closed, you can do, if you can do here, you can think of that. Find a map T R to R such that H is closed but not open. Okay, this is your exercise. Make sure that you are free to explode the net if you can't do it on that. But some of them you should be able to do it. Look at high school geometry and that coordinate, that how we're doing on that. You should be able to do it on that. Like, look, if you this, what does it mean? First of all, this y equal to x. Suppose you take that means suppose 0 into 1. It's a map. So this you get a map. I'm just giving an example that x to x. Similarly, you can have this. Look for if you want to extend to the whole of R. This is something basic technique. I can do this all this constant, and here I can do all this. That way, it will be a map from R to R, and it will be a continuous map like this. Okay. So that if in the interval you can answer these questions, then by extending you will be giving that. Okay. So you should be able to do that. It's like in coordinate geometry, how will you send an interval to this? How will you send an interval? So you can come back. This you can do. It should be a homeomorphism. There exists a homeomorphism. Basically, you need to have FA equal to C, F equal to T, and F is a bijection. And since a bijection, you'll see from the nature of the map, high school geometry, coordinate geometry, line and that. Then coming back, the inverse map will be also similar to this. Whatever you get the formula here, it will be similar to this. So automatically it will be a bijection, and its inverse will be similar to this. So you try to find out that how to do that. Okay, I'm saying it is high school geometry. You should be able to do it. Then okay, right? Well, so that this way you try that open, closed, and continuity. They are all different concepts. If they are not different concepts, we wouldn't have defined them separately. They are all different concepts. Okay, so you should do that. Okay, now look. So these I have defined homeomorphism. Homeomorphism means that you have so bijection, that means one-to-one correspondence. This is continuous, and F inverse is continuous. This is bijection, and both F and F inverse are continuous homeomorphism. And then we say that Y sigma, this is the terminology, is homeomorphic to now look, this relation is symmetric because if F is a homeomorphism, then F inverse is also a homeomorphism. F is a homeomorphism. In fact, I can write something more. If and only if F inverse also is a homeomorphism. Because I told you, don't F inverse of inverse is same math wave. So that if this is homeomorphic, then extra is also homeomorphic to this. So more precisely, you should write they are homeomorphic to each other. They are homeomorphic to each other. Okay. First of all, look so that X itself homeomorphic to itself. You take identity map. Identity. This gives you homeomorphism. Already we saw that if F is a homeomorphism between X and Y, then F inverse is homeomorphism. Also, you see that if I have this, suppose this is a homeomorphism, this is a homeomorphism. Then G dot F from X star to Z alpha is also a homeomorphism. That means it is also a homeomorphism. That property of homeomorphism is transitive. That means if you take a family of topological spaces, as a family of topological spaces. Now I'll say I will define this relation X star in this family where X star Y sigma belongs to this. If there exists a homeomorphism give a relation this family, that means this, where you have a topological spaces collections where it will become partition. Look, this is what I have exactly said, reflects it because identity map, what I discussed, symmetric and transitive. That means you get a equivalence relation. The equivalence relation is nothing but a partition. That means you will get a, I have started with a F, value of topological spaces. Because of all topological spaces, will it make sense or not? That's why I'm not saying all topological spaces. That may lead to Russell's paradox. So I'm saying a family. So you will get a partition, this relation. This meaning is what? If you have two spaces here, they will be homeomorphic to each other. But if you have one space here, they won't be homeomorphic to each other. That is the meaning. Okay. So homeomorphism is an equivalence relation. Now the look with relation to homeomorphism. So basically, from each class, I need to study only one space, not everybody. From this class one space, this class one space, and which one I will study? Which one I think easier to handle. Okay, it is better known to me. Okay, something there is, it is simpler to describe the topological space. That I will pick up. Okay, because homeomorphic, basically topologically they are same. Why topologically they are same? We'll see. Then we need to define a topological property. What is called a topological property? A topological property definition. Okay, let me write this. A property P of a topological space X star. What a property like separability, first countability, second countability is called topological or topological property. Topological. That is topological. If P is shared by any other topological space, homeomorphic to X star. Homeomorphic to X star. Like, look, separability, continuous image of a separable space is separable. So that separability is preserved by homeomorphism. So separability is called a topological property. Example, separability first countability Second countability. These are all topological property. That means second countability. You can easily check if you have this x tau y sigma is a homeomorphism, and if this is separable, this is separable, because we know continuous image of a separable space. Sometimes you need less than homeomorphism. But that's fine. First countable. You should prove that if this is first countable, if it's a homeomorphism, then it's first countable. If it is second countable, if it's a homeomorphism, then it is second countable. Okay. So that way, sometimes if you see one has this property and other one doesn't have it, last semester we did continuous image of a compact set is compact. So compactness is a topological property. So that if it is not shared by two spaces, that means they are not homeomorphic to each other. Okay, they are not homeomorphic to each other. Okay, here, lest I forget, I should tell you that in case of metric space, you have the concept of the isometry. You have the concept of isometry. So onto isometry we take. So you can take and onto isometry between two metric spaces is always homeomorphism. You should understand every subject has somewhere at the beginning. Okay, before that is all definition, elementary things. Americans say the life starts at 40. Similarly, every subject, every topic in maths starts somewhere. So topology starts actually from here. Topology starts from homeomorphism. Okay, that you should keep in mind. The isometry between two metric spaces is always homeomorphic, but in algebra, actually, they say that algebra starts at Galois theory. Okay, not before that. I don't know how much Galois theory you know. Somebody was telling he's interested in cryptology. Then you should know finite field. Here, look. Cryptology and cryptography. Essentially, they are the same thing. But if you want to do it theoretically, you need to know basically finite fields. Well, there are books specifically on finite fields, and related to you need to know Galois theory. In fact, field theory, they say it starts with Galois theory. Okay, right. So homeomorphism, but the converse did not be true. So here I want to give you an exercise. What exercise I want to give you? Look, I said this, of course, is the subspace topology. That means generated by the metric restricted, usual metric restricted to this. But to, or you can take closed interval. Look here, the closed interval will be homeomorphic, but an open interval won't be homeomorphic to closed interval. Like here, it is homeomorphic. But F is an onto isometry that you should prove. If and only if this length will have to be same. Here you are taking the usual distance metric. Look, that means unless the length are same, this for homeomorphism we do not need length to be same. Like 0, 1 will be 2 to 5. They are homeomorphic. It is a matter of translation and changing the scale. Here what you do, translate plus change the scale. You know what is the meaning of the change the scale. This way you can do. but they will never be isometric. Never isometric. Of course, with respect to this usual metric, usual distance metric, never isometric. So isometry is a stronger condition than homeomorphism. But isometry is not, that's it's not a topological property. Homeomorphism, that's we are more concerned about. So metric has something like completeness. This is not a topological property. Look here, last time I did. This will take what? Tan inverse x. This is gives you homeomorphism. But of course, completeness is not preserved. Here it is complete, it is not. So completeness is not a topological property. Okay, but that's not a bad thing. That's actually a good thing that we have that. It's okay. Okay, so make sure that previous example I have given you. This one. You should do. You should be able to do it. Okay. You should be able to do it. Okay. So that I talked about, I will briefly talk about, then I will take class on Monday. But now let me tell you that. So that here, let me summarize that. You have got open map, continuity all before you got closed map, and homeomorphism. Now I have to talk about product space. The product space, apparently a little more difficult things if you take product of an arbitrary family of topological spaces. So I will take finitely many x1, tau1, xn, tau1. These are topological space. Then the question is that on this product space, what will be the natural topology which will be related to these things, all these things, all these things. That's an, I can, this is a separate state. I can define a topology independent of that, but that is not my concern. I want to have a topology which is naturally related to this. In order to understand, look, R, we have the usual distance metric. R square also you have the usual distance metric. This usual distance you should understand. Okay, this form is different from that. But when we fall into this, this becomes the usual distance here. But how we got the topology on that? Okay, now look here. Now you have this, the basis. Writing this. It's the basis. Okay. In R square, actually, apparently we took the basis the disk, open disk, open disk. We didn't take this, but look, open disk. Now if you know a little bit of the base and that base need not be unique. So open disk, you see that I have rectangle inside, and this is contained. I think it will be a square. It doesn't matter. This. Okay. So a rectangle will be contained in the disk, and disk will be contained in the rectangle. What I'm saying now, look, if you have this in R, A, B, if I take the rectangles, You can check. This will be a base. It's a base for a topology. Tau on R square. Just you'll have to check that when that problem, that result we did, that when it will be give a topology. Those two conditions will be satisfied. Its union will be whole R square. Empty union will give you the empty set. Okay. Any point x, y, you can put inside that. And if you have intersection of this, here you should understand A1, B1, C1, D1, its intersection. Taking A2, B2, to have a point, you can manufacture that. How to do that? Okay, xy belongs here. Basically, x is here, lying in between. Y is here. X is here. So you can choose. So that means x is this. From that you can have a suitable rectangle. You can choose that. Okay, you can manipulate that. That means it will give you a base for topology. In fact, topology generated by base is the smallest topology containing that. You can have always a bigger topology like the discrete topology. Any discrete topology will contain all of them. So we are not interested in that. I said to be interested in the topology generated by the smallest topology. Now you can see that if you have two bases, now look what happens. So that, but I am saying this topology actually will be the usual topology generated by the disk. This actually will be usual topology. Well, then you need to compare two bases. Suppose X, on that set I have two bases. How will I know they will generate? And suppose this generate topology tau 1, this topology generate tau 2. How will you know that? In fact, I can ask a bigger question, that when it will be this, because other side will be the similar question. So that means you can think of that. Suppose X you have, and you have B1, B2. No, B1, B2, both are this. Okay, and they form a basis for some topologies. Tau 1, tau 2 respectively on X. But before that, you know what is base, then the topology generated by what will be the relation between this, that you should figure out. Tau 2 and tau 1 will be a similar thing. Okay, now look, when you go for a base, look, if I want to have this, look, what is the necessary condition you should have? EU belongs to tau 1. If I want to have it, then EU belongs to tau 2. Okay, that means this, if we have this, that means U can be written as a union of some members of B2. Particularly if U belongs to B1, then that should be, I should be able to write as a union of B2. Okay, then you see whether that condition is sufficient to guarantee this. That will be guaranteed, sufficient to guarantee. Similarly, each member of B2, if you can have as a union of some members of B1, you will get the other way. That way you get for the disk and that. Okay. Or, but then say, what do you mean by union and that? Look, if I get member of U Suppose V belongs to B2. And if you say V, I can recover from here, of course. If we want to have the same topology. Look, same topology, then it will be a base for that topology also. That means if we have X belongs to V, V belongs to B. But that means there exists a member P. That B has to belong to B1. If you have this, then you'll have this. And other way, if you change it, you will get the other way. That means for any member, you should check what I'm telling you. If you have take any member, you get this. There exists a member like here. Then I will have this. Similarly, I told you that intuitively smaller open sets will give the bigger topology, because union of smaller open sets, you can, if you have smaller open sets, then you can generate more open set taking the union. But if you have only bigger sets, but the number of bigger sets small than that, you can generate fewer open sets. So look here, I am getting a smaller one. So this topology will be that you should check that. Okay, so that how to compare to get this. So what I am saying, in R square, actually I could have the topology generated by this so-called rectangles, open rectangles. Open rectangles. But we do not use it because their disk is easier, in particular in Rn, disk is easier to work. Okay, these are all part of geometric topology. I am doing it on finite dimensional, but if it is infinite dimensional, not necessarily finite dimensional, arbitrary topological space, how do you use the geometries? That's a part of differential topology actually, or geometric topology, whatever you say. Okay, so that here I could take open rectangles as this. Okay, so but we take usually this. That gives you my idea of the, that means, but here look how I got this open rectangles. This sort of product topology. This gives me the usual topology on R. This is giving me the usual topology on R, another copy. Okay, that means R square, the usual topology. How I will get, that's the idea. From here, usual topology. That is usual distance. That I told you about rectangle. Now the thing is that you should check that I am leaving it to now only. Suppose you have, since I am doing only finite products, so it will be better to work with two spaces, because then by induction you can extend. Suppose you have X tau, Y sub. Now you see, you take U cross V, this collection. So it says all of them subset of X cross Y. Will it give you a topology on this? No, it won't give you topology, but it will be a base for a topology. It is a base. Even if you take all these things, instead of basis elements, if you take this, is a base for a topology. On X cross Y. Look, these are come rectangle. You can even simply see that in R square. If you take the just this, that won't give you a topology. That only will give a base. Because reason is the problem with the rectangles. How to do that? Look here. If I tell you the simple thing, suppose I have this open sets here and another open set here. I won't be able to put this way. You can see that. What will be the problem? Okay. So I won't be able to put that. Whatever set you want to pick up, you will have a bigger thing to that. If you want to include both X coordinate and Y coordinate possible, that will be a bigger thing. It won't be able, you won't be able to write this way. This one, you won't be able to write this way. Okay, so that this will only give you a base for a topology, not topology itself. But that is fine. That is fine. Okay, so this is called the product topology. Product topology on X cross Y. But you may wonder, I am getting only the base, not the whole topology immediately. It is generated by that, but this is good enough for in order to study the product topology. It is good enough just to do the base. Okay, so I'll talk about next time the product topology. Okay, fine. This is very important. Product topology on finite sets. Okay, that I'll talk about this. This will be the base, so that if you have, like, now look, if you have this xi tau y 1 I less than equal to n, then what will be the base? Base will be like this. Take this 1 un y belongs to tau y I1. This kind of thing. This is called the boxes, rectangles, you can say that. In n dimension, rectangles. This will be a base for a topology on this. Okay, this will be a base that you can easily check that. The two conditions for base on that. First condition is immediate union, it will be whole product of that. Only thing you'll have to take the intersection. Okay, then how to do that? That I told you that in R square you can think of that. This will be a base for a topology. This is called the product topology. We want to study that. This is naturally related. It is not out of nothing is coming. This is all related to this because I am defining this way. Each UI is coming from that. So naturally related to this. So whenever you study product topology, each of them, these are called the factor space. Factor. These are the factors. So these are called the factor space. So all the factor spaces will matter while this thing. Okay, that we would like to see that. But here also I should point out, I will start again on that. Now look, what will be the natural thing? Look, when from like R square to R, what natural thing you got? If you have x, y, I have one projection, that x 0. That means y, we are putting to 0, x to x. This is called the pi 1, first projection on the x-axis. Okay. Similarly, we have the second projection. In fact, topology on R square, it can be handled with these two projection maps. These are called projections. So similarly, for when I have this product, I have some people use P. Pi is the Greek word, the Greek alphabet for P, Greek letter for P. So some people write P. So here pi I will be xi. What is the projection? If you take xi here, xn going to here, sorry, or it should be, I was taking the x-axis on that. This will be x. Okay, that is homeomorphic to that x-axis. This is x, first coordinate projection to the first coordinate, projection to the y. This is, we are taking xi. Here it is called the projection to the ith coordinate. In fact, these are called the ith coordinate. That factor space also called coordinate space, like the geometry, coordinate space. So this is the ith coordinate. So product space, we have only the definition of base, and the nice thing, not the funny thing, good thing, with that base and all these projections, that B base and these projections, they give everything enough. They are the good tools. Good tools. The projections and the base. Okay, that you should know that. I will continue with this product space. Okay, see you on Monday. Okay, bye.
Sir, sir. Hello, sir.
Hello. Monday is there a class?
Hello,
No.
sir.
Monday is a class. I will take classes on Monday, both Monday and Tuesday. ठीक है?
Hello, sir.
What do you say?
Hello.
Ah.
Sir, could you please provide us notes for topology?
One node will go there, and products will later on. I will ask somebody. I want somebody people to know how to write. That is very important, because in the exam, otherwise you won't be able to write. Okay, right? Another note is pending with me because certain part he has written correct, certain part he has not written properly. So that's what second countable space, and one already I put it. My note 2 pages note. Okay, right? Surgeon fail line, but surgeon fail line I think Sanju has not written properly. So I'll have to ask somebody else. That I will do that. It is not much actually, because you already know. I think Sarthak has already written that, because second countable I have given, separability and first countable easy, and the topology that also is. So that Sarthak second countable note plus something on surgeon fail line I will post it. Okay, and product space I will do that. Okay, but before that you study homeomorphism. Okay. Okay, bye.
Sir, actually, it's difficult to understand classes with not having notes.
That you have become lazy, because last semester you have got notes, and but now I'm giving you the notes on that. Already the notes notes I am after reading. In fact, horse note one he corrected, but other things I could tell him to correct on this, but I didn't do it intentionally. I wanted the students to participate to find out. It's a small mistake. It is called typographical error, basically. Typo. Okay. Still,
yes,
I wanted
I have corrected.
So that way you should understand that. Okay. It is not difficult to understand what I'm teaching, and I am giving you the enough notes. You have the notes. You have the horse has given note, Sarthak has written note, I have given one note, another note will be there. You have the notes. It is not. I also am aware of that. What can be difficult for you or not. Okay. So that you will get. Okay. See you. Bye.